All right, so in this video, I just want to give a bit of an overview of what a Geant4 simulation comprises of. So Geant4, the name comes from geometry and tracking. So it's all about tracking particles in some geometry and scoring some quantities that we're interested in. So when we're running a simulation, so let's just go to our build directory and let's just run it with some macro run electron. So we run this simulation, we get some output. So I've got the tracking verbose in the macro set to 1, so it will spit out all the particle interactions. So we'll talk about a bit more about that later. So from the start to the finish of the simulation, so where we saw, this start here where we've launched Geant4 and it's going through the stuff, it's making the geometry here, it's then doing all the physics processes here. So the majority of what you see when you run this Geant4 simulation is just all the physics description. So it's describing all the particles and the processes and what the different models are describing the physics processes. And so that's the majority of what you see when you run the simulation. And then when you get to the end, more physics stuff, you see a bit about the geometry materials, so all the materials in this simulation. So we see we've got air, and then because of the verbosity, so for verbosity just means how descriptive something is. So if we've got a high verbosity, it means we've got a very descriptive explanation or something like that. And if we've got a very low verbosity, it means that we have a very low description, or we don't care about the details. We just want it run. We don't want to see all these details. So in this case, we've got a fairly high verbosity for the physics because we see all these different processes, and we've also got a non-zero verbosity for the detector construction because we're outputting the materials. And then after you go down, we see this. We see this run zero start. So this is when our particles begin being fired, and then we see our particle being fired in our geometry, and we see various interactions, but I'll talk a bit more about that soon. So our Geant4 run, it comprises of when we shoot the first particle. So the run started here. So when we shoot our first particle, and then it's till the end of the end of our last particle. So a run is made up of shooting at least one primary particle, or it could be hundreds, millions, or whatever. And so our run is made up of events. So one event, it comprises of the generation of one primary particle. So what it means is we generate one particle in our world or our geometry, and then we fire this particle, our primary particle, in this world or geometry, and then we look at all the secondary particles it creates in the world. And when all these particles, including the primary particle and any secondaries it generates, once all these particles either what we might call die, where they lose all their energy, or whether they leave the geometry. So if our geometry was just some square and we shot a particle in it, and if then it comes to the end of the geometry, then it's out of the world, and the simulation no longer sees it. So that was what we'd call when it's out of the world. So when all the particles are either dead, or they've lost all their energy, or they've left our geometry, then this constitutes the end of an event. So an event is from when a primary particle is generated to when the primary particle and all its secondaries are either out of the world, or the world or the geometry, or when they've lost all their energy. And then breaking down the event, an event comprises of multiple tracks. So what a track is describing the history of a particle. So this would be from when it's created to when it ends, and the end state could be when either it leaves the geometry that exists in the simulation, or when it loses all its energy, or gets absorbed, or goes through some inelastic interaction, something like that. So a track is just describing the life of a particle in the simulation. And then from that, a track is made up of what we call steps. So steps are pretty much just a collection of interactions or geometry boundaries. And for each step, for each interaction, we have a step, or for every boundary, we have a step. So I'll just show that a bit here. So in Geant4, we're tracking these particles and the interactions they have and all that stuff. So a particle's, the probability of it interacting, it all goes back to its cross section. So the probability of it interacting, and these are all material dependent. So whenever a particle is in a certain volume, or so each volume we define in our geometry, it can only have one material. So this material for this one volume, it will have a list of certain cross sections for the certain particles. So every time, if we change the geometry, if we change the volume we're in, or which means it could have a different material, it means we've changed the cross sections. So the cross section that a particle, or the probability. So remember, the cross section is the probability of a particle interaction. So that probability of the particle interacting depends on the material it's in. So in Geant4, we have a step or an interaction. A particle will have a step either when it interacts or when it changes geometry. So let's just go to the output of what I ran. So this was with a tracking verbose set to 1. What I did was I shot a electron as my primary particle, and with this tracking verbose set to 1, you can see its information. So it's got a track ID equal to 1 and a parent ID equal to 0. So this track ID means it's the first track in this event. And if we go down, we can see its step count and its X, Y, and Z. So its position in the world. We see its energy. So in this case, it initially had an energy of 1 MeV. We see the change in energy, so dE, and it has units of MeV in this case. And we see it's 0 because this is the first step. So this step number 1 is when our primary particle gets generated, and then next to it we have our track length, and that's just how far our track has traveled since it got created. So since this is just the point where it's created, it's gone 0 distance. And this also sorry, I think I skipped step length. So step length is just, how far the particle traveled in this step since the last step. So since this is where the particle or the track is created, it has a step length of 0 since it hasn't gone anywhere yet. And then we have next volume. So this is the geometry. This is the volume that the particle will be going into for the next step. And then finally we have the process name or proc name, and that's just the process which caused this step, or so this process name, I'm skipping a few steps, but this can either be a physical process, so if it's an electron, it could be some ionization, something like that, or multiple scattering, which we see a lot of these, or it could be transportation. And what this means is just when we're changing volume. So in this case, you see we were in the physical world, and then we moved into the physical phantom. So this transportation refers to changing volume, so that, as I said, when we change the volume that the particle's in, Geant4 will force a step, and then it will update the cross sections which it will be taken from. So even if we've got, let's say we've got 2 boxes next to each other in our geometry, even if those 2 boxes have the same material, then it will still force a step regardless, because as a implementation standpoint, it's much simpler and safer just to have a step occurring every time it's a different geometry than when it's a different material, because then you have to check the volume's material every time compared to just updating it. So that's what those are about. So you see we've got this electron, it's generated in this event. So remember, our run starts here. So a run is made up of events, and events are made up of tracks, and tracks are made up of steps. So, and one track, it's just the history of one particle. So in this case, we've fired a primary particle of an electron with 1 MeV, and we've generated at a position 0, 0, 200 in the world. We've got its initial energy, and then from that, from the position where it's generated, we then have our first step occurring at minus 2.59 x millimeters, then the y minus 1.35 millimeters, and then in the z 156 millimeters. So it's moved from where it was generated, and between where it was generated to its first step, and in this case it was multiple scattering causing the process causing this, and in this case, with this multiple scattering occurring, it lost 0.00574 MeV. So you can see its current energy at this step after this process has occurred here, and how much energy it lost in this process. And you see how far it's traveled until this step. And this is how far it's traveled in total. And again, if we go to the next one, we see its position. It's moved a bit more in the X, a bit more in the Y, and a bit more in the Z. And you can probably see from that, it's gone much more than it went in the first step. So in the step number 2, it went much smaller distance. So in this case, it only went 6.17 millimeters, and you can see how much energy it lost. So it lost a bit less energy, so about a fifth or so of the energy in the first multiple scattering interaction. And again, you see how far it's traveled in total. And then you see in the third one, it's reached the end of the physical world, or well, not the end of the physical world. It's reached the start of another geometry called the physical phantom. So in this case, we've just got an air box world, and that's 1 meter cubed. And inside that world at the center, we've got a water cube 30 centimeters cubed. So you can see at this point of 150, since our phantom's 300 millimeters, and since it's placed in the center, so it, as you'll find out, or you may already know, Geant4 deals with like half volumes for many volumes or shapes. So our water cube or water phantom placed in the center of the world, which is 30 centimeters cubed, it extends from minus 15 centimeters to 15 centimeters. So you see now that we're at Z 150, we've reached the boundary between our air world and the water phantom. So as I said, whenever there's a boundary between volumes, Geant4 will force a step, and that's when we see this transportation. So now we've got the cross sections for water occurring. So you'll now see with step 4, we're in the physical phantom now, and again you'll see our X, Y, Z positions, its current energy, and how much energy it's lost. So this energy loss of 0, this was 0 because it's updating the information from its location from being in the air world to now the water world. So it hasn't lost any energy, it's just changed the volume. So it's, if you like, it's in the same position, but it's just updated where it's taking that geometry, that cross-section information from. So now it's taking it from the water volume instead of taking it from the air cross sections. So as you see, we didn't move much, and so on and so on. So we just have all these multiple scattering events occurring. And then if we go all the way down to step number 21, it's doing the air phantom, then we've got this electron ionization occurring, and another electron ionization occurring here. So we see these energy losses of 417 of 0.0417 MeV and 304, and so forth and so forth. And in this case, we didn't see the actual electrons generated from this ionization, and that's because our electron cut was below the threshold needed. So these electrons that would have been generated are below a production threshold we're seeing in the simulation. So I'm not sure what we set it here. Actually, we can just go up here, and you see we've set a production threshold of particles set to 1.03 centimeters. So if we go here for the electron, an electron requires 2.2 MeV approximately for an electron to have a range of 1.03 centimeters. So these are the energies we've currently seen in the simulation. So a particle won't get generated unless it has an energy larger than this value here for this geometry in the water box. So in this case, if we go to where the ionization occurred and we go to the DE MeV, so the energy change, so in this case, the electrons were all below 0.2 MeV easily. So what was we needed at least 2.2 MeV. And as you can see, all these electrons were way below the required energy of 2.2 MeV. So in that case, the simulation will just treat all this energy as just being locally deposited. But if one of these electrons was above this threshold of 2 MeV, then it would have created a new track and actually generated a new track and tracked that electron. So if I actually just go here, I've got a track, or sorry, an event I prepared earlier. So in this case, we shot an electron again with 1 MeV, but in this case, we had a lower cut or production threshold. So instead of having 2 MeV, I think it was set to 0.1, or was set to the length was set to 0.1 millimeters. So the required energy for an electron before it would actually be generated was much lower. So in this case, we've just got an electron ionization occurring at what was the energy here? So 0.0024. And if we go down to the